There we go. Now it's on. Okay. Yeah, so I want to connect the ideas of, connect the ideas from machine learning that we've talked about for learning models with some of the sort of, I'd say, deep insights that happen when you have the model you're trying to learn is governed by multibody equations, by physics. There's so much extra structure. So let's dig in a little bit. So when we talked about behavior cloning, this is sort of before, right? I went through sort of the spiel that you should think about your policy here as a dynamical system that takes in observations, streams of observations, and produces actions, right? And the great thing about behavior cloning is it formulates the search for policies via supervised learning, right? But because this is not just a static function, this is not just typically not just a feed-forward network, it's a recurrent network, or it's something that looks at histories of observations, this is really a sequence learning problem, right? You have to think about actions or observations that might have happened in the past affecting the current action coming out. Or the other view of it would be that given whatever here, I might have to predict a sequence of possible actions, right? It's sequence in, sequence out. And so in general, these policies are dynamical systems, which are written potentially in state space form. Right, where alpha is the parameters we're trying to find. Could be the weights of a neural network. And the goal of behavior, the optimization we do in behavior cloning, the goal of the supervised learning is to find the alpha in order to predict, to learn that map from observations to actions. Right, and we talked about a handful of different ways you could represent that. You could talk about it in state space models with recurrent networks. You could use transformers if you wanted. Maybe you use diffusion if you're trying to learn for stochastic policies, for distributions over actions. Okay, but there's also sort of a more classic view of this learning. You could learn it as a linear system if you wanted. For instance, if you learned a linear state space form, then we know a lot about how to find A, B, C, and D in order to sort of map these long-term, find these sequence problems. Okay, and so there's actually a lot of important lessons that can be learned, even though this model class is not maybe rich enough to handle what the things we want to do with diffusion policy, right? The clarity, I think, of the simplicity of these equations helps you think a little bit more clearly about the long-term implications of solving these problems when stability is a factor and other things. Okay. So that's kind of what we talked about a little bit before. But today, I want to say we want to do pretty much the same kind of thing. Okay, but this time I want to learn the model of the plant, right? So now I have actions coming in and observations coming out. Okay. On the surface, you can do all of the same things. Like it is absolutely everything we did here is still relevant for modeling the plant. Okay. But maybe there's like one new option or one new set of options which would be the physics-based models, right? Right? If we're working with things that we know are governed by Lagrangian mechanics, then there's extra structure we can put on our optimization, which will make this problem more tractable, first of all. But also, again, in sort of the same way that the linear system thinking helped us see more clearly, I believe you can see a lot of things more clearly by seeing how we do things in the Lagrangian setting. And now there's active research about how do you pull the sort of physics-based reasoning and do physics-inspired neural networks and things like that, okay? So my primary goal for today is to give you a little bit of the, a few of the lessons from physics-based identification, okay? There's some beautiful things about it, maybe some surprises, but I'll try to emphasize the lessons that I think could generalize, even if you don't. So it'd be immediately useful if you want to identify your robot, you know? It will, and I think there'll be lessons that generalize if you want to identify the state of the salad, you know, or something more complicated. We'll see. Is that setup kind of clear? Maybe one other thing to point out, right? If the goal is to have, you know, a plant model for control, then that actually also changes the problem a little bit too, right? So if you, let's say I could perfectly match my actions to observations with a massive transformer, okay? But maybe then I don't have as many strong control tools to work with it, right? So typically if you have your dynamics, maybe say trapped in a huge network, then your options are you know, typically either do reinforcement learning to find the policy or do some pretty weak sampling-based trajectory optimization. If you've heard of MPPI or CMA kind of optimizations. But the amount of things we know how to do well for control, if that plant is a massive network, are pretty limited, okay? So you might choose to take a more impoverished class of models, let's say physics-based models, because we know how to do better things with control, right? Or you might have seen people talk about, I don't know if we have anybody from Harry Asada's group, but Harry's really excited about the Koopman operator stuff. So maybe you want to learn an underlying linear system that is maybe high dimensional, but because that's an easier system to do control with. Okay, even if the observations, the mapping into and out of that linear system are nonlinear transformations. Okay, so I think another interesting thing about these models is just that they're good for control. I think the linear systems are really good for control. I think the multibody systems are sort of in between. We know a lot of good control, some of we've talked about in this class, and they're stronger than the general neural networks. Okay, so let me motivate that maybe with a specific example. So all of you who are in the CIM component or started in the CIM component, I think many of you read this tossing bot paper at the beginning of the year, right? So imagine the problem of trying to learn the dynamics of some object so that you can toss it in the bin, okay? This is a beautiful paper. I think the writing is great. That's one of the reasons that we use it in the journal clubs in the CIM section. I think the experiments are great. You see the task, have your robot arm, pick up an unknown object, throw it in the bin, right? My favorite part of it is the way they reset things. Have you guys seen this video? Right? Okay, good. Yeah. This is the best part here. Where do they reset it? There you go. See? That's perfect. I love that. Super clever experiment design, right? And if you're going to do learning and you want to throw lots of objects all day long, then that's a pretty good way to go. Okay? So let's just take that as a motivation. I've got a particular object. I want to estimate it and throw it accurately in the bin. Okay? Actually, so this was a sort of a neural network version. If those of you that read the paper remember that there's a neural network representation. They use a little bit of physics, but they emphasize in the paper to learn a residual model of the difference between the simple model and the actual rollouts, sort of, and they learn a neural network model. But there's actually an older version of this project that maybe most people haven't seen. It's an MIT, come on. This is from '91, from Jean-Jacques Slotin and his lab, okay? It's a whole body manipulator, or the WAM, whole arm manipulator. Okay, it's similarly picked up objects of unknown mass, unknown geometry. Okay, but it could like chuck them into a target across the room every time, you know? All right, so let's just watch that one more time here. Think about how it does that. Right? That's a 91. Okay. So they're solving different versions of the problem. So it's a little bit unfair to put them next to each other. Okay. So the tossing bot has got a more general, more flexible representation. If there was aerodynamic effects in the banana it was throwing or something like that, the approach in the Slotin version wouldn't have addressed that. Okay. But in the cases where the multibody equations, the simple ones you write down, are a good description of the dynamics, then this approach works incredibly well. Okay? Now, the tossing bot threw objects all day long in order to learn its model. It took many touches of the same object in order to learn models in order to throw. This one, you take a new object it's never seen before, it goes like this, partly to wind up to throw, but actually, that motion is enough for it to do the estimation of the parameters in order to throw it. Done. It's like zero-shot generalization in the world of RL, right? Or learning, right? So in the case where we know the multibody equations are good, we can do way better than just jamming things in a massive network, okay? And this would, a new object, again, just one motion. So let's just think about a little bit about the multibody version. Okay. There's a subtle point, right? The dynamics of throwing are a little bit. It's just sort of worth commenting on that real quick because if you think about the point like after releasing the object. Then the dynamics are trivial, right? So you have the mass plus the center of mass dynamics in the x direction are 0. The mass times the z center of mass dynamics are negative mg. It's going to rotate, so there's some inertia written around. Let me write it in the proper multibody notation here. Right, so there's conservation laws happening when it's in the air, okay? But this implies that since the mass we know is positive, right, basically it's just not accelerating when it's horizontally, right? Z center of mass double dot is just negative g, okay? And then theta double dot is also, we have that it's 0, okay? So if you think about this as effectively the governing equations of the body, of any rigid body flying, ignoring aerodynamic effects, okay? They're, not only are they simple, linear, okay, but they also don't depend on any parameters, right? As long as you know gravity, you're done. You don't have to estimate the mass in order to have the ballistic trajectory, except for the initial conditions, right? So what matters, in order to hit the target is not the arc it follows. That's trivial once you know it lets go. What matters is that at the moment of release, your center of mass is going in the initial velocity and position and velocity that you need it to be, right? So you need to know the center of mass of the object very well. If you care about orientation, you need to know its inertia well and be able to think about that at the moment of release. There's also, a few of you are thinking about throwing and catching kind of things in your project. There's some subtle, I mean, the dynamics of opening your fingers is actually pretty subtle, right? So the contact, you'll have friction, and then the friction will reduce, and then it'll go to zero. And it'd be beautiful if that was instantaneous, but that's not how it works. So in that work and in other throwing and catching work, people typically design trajectories that align with the motion you want the ball to have for some amount of time, and open your, assume that the hand is quick, but no matter when it opens, in that, because of delays or limits in motor speed, you'll be on the path that you want the ball to follow. So there's subtleties like that, okay? But most of the work in estimating the parameters determines both the takeoff conditions, and if you're doing careful control, like the whole body manipulator is doing excellent trajectory tracking, model reference trajectory tracking. I think the tossing bot is just a position controlled robot, and it's kind of doing its thing, and they're trying to learn any of the compensation. But remember, we talked about manipulator control. We said the more of the terms you can cancel out, the better trajectory tracking you can do. So if you want to really hit a target velocity extremely well, then you actually want to be telling your robot controller about the mass and inertia of the load in order to cancel that out and then hit the target really well. So it determines the takeoff condition plus the trajectory tracking controller. Again, for simple trajectory tracking, you don't need that level of fidelity, but for exquisite, like throw a ball across the room and land in a hoop the size of the ball, then you do need that kind of fidelity. Okay, so let's figure out how we're going to estimate the inertial parameters of the ball. I'm going to, this full problem talks about all the way to observations. But let's just say we have perfect state observations for today, when we'll see. That's an assumption, but let's just say we have perfect state observations. So let's say I'm given state observations. So let's say I can measure Q of n. I'll even pretend it's a continuous trajectory, because that'll, okay. Q of t, I can estimate nicely Q dot of t, even Q double dot of t. And since we're using our EWA or our whole arm manipulator, we'll have torque measurements too. The goal is to estimate the mass, the center of mass, and the inertia, moment of inertia, yeah. for the object. Okay? And again, we're going to get to the point where we're in a low data regime in order to do this. Clear? Okay, how do we do it? Well, first we have to choose how we're going to parameterize those. Even if we want to, if our goal is to learn the mass, center of mass, or inertia, we could choose how to parameterize it. Okay, it turns out the way you parameterize it matters. Okay, there's a natural one. So if you look in the URDF, right, you specifically get to say what is the mass, what is the inertia, right, all these things, okay? But it turns out that there's the slightly more natural parameterization is actually to think about the mass, the first moment, and the second moment. I'll show you here. So let's just think about mass, okay? Mass is can be computed, given the density of the object, if you think about it, as basically the triple integral over the volume of the object of the density. Yeah? Is that notation okay? It's a little bit sloppy, but I'm just going to integrate the density. Yeah. So let's think about a quantity like this, okay, which is the first moment of the density-weighted first moment, okay? Okay, it turns out that this thing is like the mass times the center of mass. So if I say in the body coordinates, okay, this is just a scaled version of the center of mass. So you could try to identify the center of mass directly. It's slightly more natural, actually, to identify mass times the center of mass. Okay? And then inertia, it turns out the second moment is basically what your inertia is, right? This is kind of a different way to think about moment of inertia. Okay, it's your second moment of a density-weighted second moment. And the actual moment of inertia that we normally talk about is basically that. It's a small transformation of that. It's like you can just go back and if you have this, then you have the moment of inertia. That equation is all that's important about that is that it's linear in the sigma. Okay. So think about a nice way to parameterize the inertia is actually in the moments of the density. Okay. So the mass, this quantity h we're calling it, and this quantity sigma. The 0, I guess, first and second moments of the density-weighted moments. This thing we know is symmetric. So this one lives in R3, right? It's a 3-element vector. Yeah. This one it's a 3x3 matrix, but it's also a symmetric matrix, I guess. Like this. So in total, you can parameterize your 3x3 symmetric matrix with 6 numbers, yeah? So in total, you have our parameterization is going to be the mass h, which is 3 numbers. This is 1 number. And then sigma, which is 6 numbers, okay? That's a beautiful way to parameterize your inertias. It turns out you can't pick any 10 numbers and get a valid inertia. You might get things, the fact that density is always positive basically puts some constraints on what these numbers are. We've over-parameterized it with those 10 numbers. So that's maybe the first important lesson, is that you can add strength to your system identification by knowing things like mass is positive and inertia is therefore is created by mass. And so therefore you can add additional constraints. Some of you know about these constraints because you found a SDF online, you stuck it into Drake, and Drake said, that's not a valid inertia, right? Sorry. But that happens a lot, actually. So there are some rules that if the inertia is going to come from a physical object, then it must satisfy. It turns out, and this is due to Pat Wensing, who's some of you might know that he was in Songbei's lab before. Now he's an established professor at Notre Dame. He's the one that sort of showed that in these parameters, the complete characterization of physically real inertias can be written as a positive definite constraint on those variables. Okay. Turns out this is a PSD constraint, which implies you have a semi-definite program. If you don't like semi-definite programs, which is fair, then you can make approximations of that. Okay, but that's sort of the real constraint, is that if you're going to search over all the parameters of your inertia, you should search on them subject to that constraint. There are other nice physical constraints that you could put. For instance, if you know sometimes we try to identify objects that are from, we're trying to identify the parameters of our robot, and maybe we have CAD models of our robot, but we don't know exactly what the inertia ended up being, right? So you can add additional constraints like the center of mass should be inside the convex hull of the geometry. That's a strong thing to be able to say. You can even put a bound on the second moments based on the geometry of the object, too. Okay, so you might just want to say mass is positive, for instance. That's another very useful thing to say. And it's an interesting lesson because what you will do is you write a beautiful algorithm to do system identification. You will avoid that constraint, and then you'll estimate things, and you'll find out that the mass was predicted to be negative. It happens all the time. Or it says the center of mass is somewhere completely, just because of out of noise artifacts, or something like this, right? If you don't put those constraints, then you'll typically, especially in the high noise or low data regime, you can have problems. Okay, that's pretty elegant. Yeah?
What is this J matrix called from physics? Is there any notion associated with, or is it just?
Patrick's papers call it a pseudo-inertia, which I think is maybe an admission that it doesn't show up in physics or something. But I actually think it's the more natural term. I mean, this is like a beautiful characterization of what it is. And the inertia is a small transformation away from it. But it's typically called the pseudo-inertial matrix. Yeah. Okay, so let's say you don't like semi-definite programming and you like gradient descent and PyTorch. Okay, I would forgive you that this day and age, okay? So you could try to say I'm going to impose that by default, right? If I were to parameterize this with upper triangular matrices, you can impose the same thing sort of out of the box, the way that Patrick and company propose to do that is a parameterization like this. This is an upper triangular matrix. Okay, so this is the exponential, right? So if we parameterize it in with some functions such that the diagonal entries can never be negative or 0, right? And we say that the matrix is always positive definite. Then you can search directly in the parameters of alpha d1 s t with gradient descent, and you will, by default, you now have a non-convex problem, okay? But because it's actually a smooth transformation from these variables to the original variables, if you don't add additional terms, you can actually still guarantee this will converge. Okay. But you could do it with, you could solve with gradient descent. With some guarantees. With your PyTorch toolchain. Okay. I actually asked Patrick about that. I said, okay, you wrote this paper, you wrote that paper. Which one would you actually use on any given day? He said, if you're afraid of SDP, then do this. But if you know SDP, just do that. That's way better. For subtle reasons, because I think a lot of times these constraints are actually active at the solution, which means that these parameters are like going off towards infinity. And so gradient descent is actually kind of a hard thing to make work super well on some of these problems. Even though it will work, the numerics of it can be bad. Okay, so that's maybe a little bit about how to parameterize inertia. And that's lesson 1 is careful parameterizations go a long way. Lesson number 2, and this is, I think, a big one. I think it's super relevant in any model learning problem, but people don't, I think don't know all the lessons from SysID, maybe. I will call it equation error versus simulation error. Okay, so the cost function you pick matters, right? So what is your loss function for ID? Let me just define carefully what I'm going to write here in a second here. So I'll use this notation for the prediction. Right, that's our standard notation. And so I'm going to use this as the data, okay? So you have a choice when you write these optimization problems down about what's the loss function, right? And if I keep it in the high level of x, of this sort of form, and I have observations of x and u, then how am I going to formulate a system ID problem on F? The equation error version of it would be, I'm going to find the alpha such that I minimize there. Okay, that's a pretty reasonable thing. Okay, but let me just write down the simulation error as a different thing, which would be I'm going to minimize over alpha Okay, those look similar, but they are actually very different. Maybe I should do it first, best with a picture here. So the equation error is a one-step error, okay? In the sense that, let's say I have a real data trajectory that has, I've gotten some maybe noisy measurements of, but I've gotten some data like this, which this is x0, this is x1, x2, x3, and so on, right? The equation error says I want to pick a model so that if I start anywhere on this trajectory and I take one step, I'm going to penalize the difference after that one step with the next model, or with the next data point. But when I get to the next step, I'm going to reset the model, basically, between every step, and I won't have compounding error from my model. I'm going to just sum up the one-step errors. This is my equation error, which is one step, no compounding error. The simulation error is a tougher metric. Okay? It says if I start here, I'm going to roll out the entire trajectory, and I'm going to penalize on every step that difference, right? But small errors could potentially accumulate, and this thing could go far away if my model is bad, right? Actually, the model has to be pretty good to follow that well. Okay, so the simulation error evaluates my ability to do long-term predictions with compounding error. Yes, please.
What if I would define a residual trajectory?
Yep.
And say my trajectory is not like x1 to xn, but I just do xn minus xn minus 1 at each step.
Mm-hmm.
And then wouldn't that be equivalent?
I think, yeah, I think so. Yeah, I think you could rewrite this as having basically another variable here that has the one-step prediction. But I think that would turn out to be, if I understood you correctly, I think that would turn out to be like the equation area.
Yeah, exactly. What I'm trying to say is that like you could, like it depends if you change your trajectory space.
Okay.
Kind of
Yep.
one is the other.
Yeah, fair. But I think fundamentally these are two different objects, right? Whether I can predict, a long rollout successfully or whether I can predict one step successfully. Those are completely different objects. So I think you can change variables around, but you can't hide or not hide the compounding error, right? Do you get f of f of f of f of x, or do you just get f of x in your objective, right? And the lesson is almost always that this tends to be easy to optimize. In many cases, it's convex. This one is harder to optimize. This one tends to be non-convex. But this is probably the one you really want, right? This is the one that, it's a harder objective. If you can satisfy this, then you've got a good model. What's interesting is you can get a very low error on the one-step error and still have an arbitrarily large simulation error. Okay, so in particular, that happens if you're learning models that are like on the boundary of stability. You could have something that had an arbitrarily small equation error that learned an unstable model, even if your data is stable, and then the simulation error could be arbitrarily large. Yeah? Okay. So that's a super important thing. Now, the equation error is, like for linear systems, it's convex. Maybe what's surprising is that even for multibody equations, we can actually write a lot of convex optimizations on the one-step error, but there's no hope of doing that for the long term. Yeah?
So in order to go from equation error to simulation error, can we start with a small dt and then gradually increase that dt? Because when you have 1 point for your whole trajectory, that's basically simulation error, right?
Okay, yep.
And when you have endpoints, it's equation error. So
Yep. I think the stretching out the time with like an Euler approximation of the dynamics would not be rich enough to capture what's happening in the rollout of many steps, right? I think fundamentally, like in a discrete time setting, the question is if you have like x of time 4 is really f of f of f of f of x0, u0, right, u1. You can't capture that with a longer dt on Euler, if that makes sense. Okay, if you do higher order, but then you're either approximating f to get that higher order integration, you're evaluating f at more points to do that. I think you're fundamentally either have to go embrace that or not, right? Yeah. And we have strong theorems, like especially in the linear systems case, we know, for instance, that the one-step error can be arbitrarily small and the simulation error can roll out. So there must be a fundamental difference. You can have an arbitrary small equation error, an arbitrarily large simulation error. Now, having said that, if this is a complicated optimization problem, and this is an easy one, maybe this is the one we really want to optimize, but this one's easy. You can often use this as a first step, get a good initial guess, and then refine it with the non-convex. And maybe you're in the basin of attraction of a non-convex optimization, you just dial it in and get the longer term prediction. Okay, when people do sequence learning and learn neural network models, I think they will often do the one-step error, but miss the fact that that one-step error, especially if stability is an issue, can be arbitrarily bad in the long term, right? It's just kind of an easy thing to not know unless you've thought about the SysID versions. Okay, so it's convex in the sort of linear system case. It turns out what's surprising is it can be convex in the multibody case, but you have to know what you're doing. If you just take your simulator and evaluate the one-step dynamics through the multibody equations, then it's actually not going to be a convex optimization, but you can change coordinates and make it a convex optimization. Okay, so I'd say lesson number 3. use the inverse dynamics not the forward dynamics. Okay, that's maybe surprising, because if you just take this view of the world and you say, I'm going to minimize this, right, that would have you using the forward dynamics of your object. And that's the wrong thing to use if you have a Lagrangian system. Okay? So what do I mean by that? So we know our favorite multibody equations. Okay, this is actually the inverse dynamics, right? In the sense that if you tell me q double dot, q and q dot, this will help me solve for u, right? If you want the forward dynamics to simulate forward, then you actually have to solve for the mass matrix inverse times the rest of that thing. Right? This is the forward dynamics, which gives me from q, q dot, and u tells me what q double dot is. And if I were to take an Euler integration of that, this would be the one that looks like this form, right? Okay, so here's a cool observation, an amazing observation, I would say, is that if you take the way we parameterized the inertias and you put them in this equation is actually affine. It's convex in the inertia parameters. Okay? This one is convex in the inertial parameters. The second one is not convex. This thing breaks the convexity. This one is non-convex. And in fact, most of the parameters we would want to identify, I listed only inertia so far because of my simple example, but if you want to estimate the joint frictions or other things, a lot of the relevant quantities are actually appear in an affine way in this equation. Okay? And they don't appear in this equation. So that's interesting, right? If I'm throwing a neural network in there, and I'm optimizing what you would be a totally reasonable standard parameterization of my system ID problem, then I've made the problem worse than it needs to be. If I just multiplied both sides by the mass matrix, then I get a problem that's convex again. Okay? So a lot of lessons, I think, that come from this. Okay? So because this thing is linear, let me just shuffle my papers for a second here. You can almost always rewrite our dynamics as linear in the parameters, okay, or linear in the lumped parameters. Let me take a super simple example here. So if I have a simple pendulum, okay, which has got a length L, a mass M. I mean, this is sort of too simple to be representative, but just to give you a sense of what I'm saying here. Okay, so those equations, maybe you guys could, so these equations, the terms you care about estimating, appear linearly. Okay. This one, if I were to divide m by m through, it wouldn't make a difference because it's a scalar. But as soon as I have a more complicated system, this is still true. If I come up with equations, and I have some thrown up here, of, let's say, the double pendulum, okay, I get a slightly more complicated set of equations. But still, the masses and the inertial parameters always enter linearly in the complicated multibody equations. That's remarkable. Okay. It turns out if you're trying to identify both the masses and the lengths, you probably shouldn't do that because there are other better ways to independently estimate the kinematics. Okay. But if you wanted to, you can also identify them jointly. And then the systems are linear in the lumped parameters, it's called. I linked in, I don't know if anybody noticed, but in the schedule I linked to some notes that I have some sysID notes that talk about how you decompose the and can make the multibody equations linear in the lumped parameters. Okay? But that's sort of remarkable. Like all of the data comes in through nonlinear functions potentially. That one's the only one in this particular example, but the data comes in through this. But you'll never see in any of the multibody equations anything that looks like this, right? The masses never sneak inside the hard nonlinearities. You get L squared and stuff like this, but you never get mass squared. Okay? There's a structure in the equations that makes that an easier optimization, which is beautiful, right? So that means in order to estimate our parameters, which we said we're going to do mass, h, and sigma, okay, then I can actually write this as a least squares problem. Okay, where alpha is these parameters vectorized, right? I was using shorthand. I would want to vectorize each of those. Okay, stack them into one long vector. W is my data matrix, just like we saw in ICP. Okay, where every data point gives me a new row of the matrix. Okay. So every time sample gives me n equation, n rows for n doth robot. Okay? But I really, in the inverse dynamics form, I have a linear problem to solve, a linear least squares problem to solve. Okay? So what I can do is now say I'm going to minimize over alpha, w alpha minus b squared, something like this. That would have a closed form solution. But if you solve this problem and you get masses that are negative, then you might do better to also put in that constraint that j, which is a function of alpha, but a convex function of alpha, is positive definite. Or mass greater than 0. You can start adding those extra constraints. And still, this is a convex optimization problem. Right? This is amazing, like that you can fit the multibody equations of a arbitrarily complicated robot in the equation error setting as a convex optimization problem. I think it's incredibly beautiful. Of course, I have a notebook that does that. Let me show you. I just took the simple system here, the canonical system, yeah, a two-link robot. Okay, the equations here are simple enough that I can print them out. Okay, again, the mass enters. It's linear. It's affine. The total equations are affine. I can just generate a bunch of data by simulating a bunch of different rollouts. If I start the notebook here. Okay, so I just ran some random sinusoidal inputs into my one actuator in that cart, okay? Generated a bunch of data. And then for every point in that data, I'm going to add one, I guess 2 rows, since it's 2 degrees of freedom, 2 rows in the data matrix. And I'm going to solve a least squares problem. Okay? And I can estimate, if I extract from the URDF that generated the data, I did a very low data regime here, just a few trajectories, but I get very good fits of the true parameters coming out. And this actually estimated the masses and the lengths simultaneously, which is trivial in this setting. Okay, so it's just like a few lines of code. It's really just make your data matrix, call least squares in this setting. Boom, you can solve the problem. Yes? Yep, good. So yeah, in the inverse dynamics form, I've got my discrete data, so I need to do some sort of a discrete filter in order to estimate from, let's say, a trajectory of q's. I'll pull out q dot, and then I'll differentiate that again to do q double dot. In this case, it's notable. So we've said in the past that q double dot should be maybe avoided. It's a noisy thing, okay? And actually, some of the parameter estimation for multibody tries to avoid it. In the setting where you're doing offline sysid, though, then you can do arbitrarily good sort of acausal filtering. And I think people are less worried about using q double dot in the offline setting than on the online setting. But if you're doing online estimation, which people definitely do, then maybe avoiding q double dot, some of the different parameterizations that avoid double dot can be good. There's a way to basically take an integral over those equations. It's like they call it the energy-based formulation, and you can integrate away q double dot and work directly with q and q dot only. Yeah.
About the form over there, like below there.
Yep.
I just had a look again at like Wensing's paper.
Yep.
And he actually includes the mass in the pseudo inertia.
I wonder. Okay. So it's.
So you need to have the additional.
Yep. Is it in the fourth?
Oh, you have the one.
Yep. But you can make that a mass. Yep. Yep. Good. So that could be implied by that. Thank you. Yeah, I couldn't remember actually. I should have written it down. So it's like this would be the pseudo inertia. Yeah. Thank you for catching that. Yep. Good. Okay. So I think that's pretty incredible. I mean, you could have, in fact, so Patrick worked on mini cheetah when he was here. And he's got like a lot in his papers. He actually has data fitting mini cheetah, right? The actuators and everything like this of the mini cheetah. You can also take this observation. You can add in things like joint friction, rotor inertia. There are other things that you might want to estimate that fit in an affine way into this set of equations and can be included in the least squares estimation formulation. Okay. All right, lesson 4 here. Okay. Even inertias, I could say, so if we extend the case, So if we're only estimating the mass of the object we're about to throw, then this is not a, then all of those parameters should be estimatable, identifiable, assuming you have a sufficiently rich arm, 6-degree of freedom arm, then you should be good, okay? But if you're trying to estimate the inertial parameters of the arm, which is a big part of the exercise here, then actually you can't populate all of the parameters in the URDF. Okay, you're actually spending time entering your URDF with parameters that could not possibly be estimated from data. Okay, so as an example, the inertial parameters of EWA link 1 when the EWA is bolted to the table are completely unavailable to you, except, you know, so you can estimate, for instance, if the EWA link 1 is actually the rotation around Z, then you could estimate the rotation around Z, but the rotations around the other axes, for instance, the moments around the other axes are not identifiable. That makes sense, right? Nothing you can do waving your arm around will tell you about the inertia of your first link because it's bolted to the table. And actually the second link, you only have 2 degrees of freedom, so there's two things you can estimate, but not all 3 you can estimate. Okay, so if your goal is to populate the URDF perfectly, then the torque sensing on your robot is not sufficient to do that. So you could take this moment to be like incredibly disappointed, and or you could embrace this and say, those parameters are completely irrelevant to the dynamics, and I don't need to know them, right? The reason that they're not identifiable is because they don't matter. They don't affect the outcome of your dynamics. So you can just put whatever you want in there, right? You could call the inertia around the x-axis 42, and it would not affect your simulation. Okay. However, if you're solving least squares problems, you should at least you need to acknowledge that that could happen in order to make your least squares problems well posed. Okay. So like, so how do you should this change? Because what could go wrong, right? So we worked hard maybe to put a triangle inequality or this pseudo inertia matrix as being positive definite to make sure that things are physically real, okay? But if it can set some numbers to be completely arbitrary, then it could cheat us on the parameters we do care about. It's destroyed the strength of those relevant parameters. So there's a couple ways that people address this. The classical way, or maybe I'd say they're both classical. First thing you can do is just explicitly take them out of your optimization. These potentially problematic parameters, just figure out where they are. There's multibody, there's algorithms that can tell you which ones can't possibly be identified, or you could actually do it with the data, right? So if W alpha has a null space, if W has a null space, then it can basically tell you which parameters your data did not properly excite. Okay, and you can just remove them from consideration, solve a smaller version of the problem, and avoid numerical challenges. Idea 2 would be to add a regularizer. So we'll do a minimize alpha W alpha minus B squared plus maybe some distance from my, let's say, original guess from CAD models or something like this. Okay, and this is some sort of a distance. And probably I'll put a scalar on here. That's some small coefficient. Okay, so that way, you know, the idea would be that if beta is small compared to your data, then most of the optimization mostly thinks about this, but sort of in the null space of the optimization, then this small term helps you center your original parameters around the known, or your initial guess of the parameters. You can think of it as adding a Gaussian prior or something like this to your least squares problem. But there's actually a lot of nice work that's happened, again, in the last few years, of trying to figure out the right way to write those regularizers, so you have geometric consistency and you're respecting sort of the interesting, rich geometry of the inertial parameters. Okay, I mean, that's like maybe the 4 big lessons, right? That if you have multibody equations in this sort of canonical form, then it's not only that you can do better, but if you do the standard sysid thing and you just treat it like a black box that you're trying to fit, you've made the problem like way harder than it needed to be, right? It actually took a convex problem and made it non-convex because you're working in the wrong coordinates, for instance, okay? And there's just all these gobs of structure that if you manage it correctly, you get convex optimizations out, at least for the one-step error. Okay. So there are a handful of other like interesting ideas that come up. Let me name 2 of them. One of them is optimal experiment design. So it becomes a real interesting problem to say I'm going to try to identify the object I'm holding, or maybe the entire inertias of my arm. What motions should you move your arm through in order to get a good system ID data set? Okay. In general, that could be a hard problem to think about. But the linear structure of this gives us a bit of a handle on that. Okay. So in the case where we're writing these sort of least squares problem, then what you'd like to have is something about the condition number of this W matrix. Okay. If you've got a data matrix that is sort of nicely conditioned, then you're going to have a good least squares problem. So one of the ways people do this is they'll actually try to solve a trajectory. I mean, some people just run sinusoids, and that's pretty good. Okay, that's actually pretty good for a lot of cases. But a slightly more elegant, especially if you want to do something efficient, let's say, is you can actually try to optimize the condition number of the W matrix. right? So if you're, let's say we're in the case of we're identifying the entire arm, right? So maybe you're in the luxury of where you're in the lab and you can just let the robot move around all the time. There are more subtle cases, right? So like the Slotine case where it just did one motion in order to estimate the parameters and then through, that was a pretty elegant minimal design. And there's everything in between. Like maybe we've talked to Amazon Robotics about, for instance, you know, they're moving packages and they want to identify the parameters of the package, but they don't want to take arbitrary trajectories. They still want to move the packages from A to B as efficiently as possible. So could you like make minimal excursions from the nominal trajectory that add a little bit more informativity to the data in order to excite some of the parameters, but balance that with minimum time objectives or something like this, right? So there's very nice sort of problems sitting in there. And maybe oh yeah, please.
Quickly about that example.
Yeah.
Why would Amazon be interested in that? Why would they? Why do they know that? Why wouldn't they need to know the parameters?
Yeah, it turns out the limits of speed of moving boxes, let's say, depend on the dynamics of the object, right? So both, I mean, you could be up against saturation limits on your robot. That's in the best case. Maybe it's more likely to be the interface between your robot and the object. You don't want to throw a package, for instance, right? So yeah, so I think having the better your estimate, the closer you can be to the limits of performance and move things faster, right? Yeah.
To what extent can like a greedy sort of sensitivity
It's a good question. Yeah, so I think the question is, if I'm just on the fly seeing that some parameters are not being excited, I could just like, you know, in a local sense, a greedy sense, you say, try to excite some of those parameters. My sense is that there are really parts of the parameter space, of like the configuration space of the robot that will be, I mean, there are cases where people try to estimate things by like moving the robot to canonical poses, right? Because you can excite the parameters in different ways in different physical locations. That would be an extreme case. I don't know. It's a good question. I mean, how much could you excite? It probably depends on what kind of frequencies you're allowed to send through your actuator and stuff like that, right? Yeah, it's a good question. I think in the limit, with perfect sensing and infinite bandwidth, then you should be able to identify anything like arbitrarily close to your trajectory, right? So I think that the answer comes through those more subtle things of like you don't have infinite bandwidth and you have noisy sensors. Yeah. All right, last point is that you can do online parameter estimation. Which is often called model reference or adaptive control. So the heart of that Jean-Jacques Slotine example was actually on the fly formulating the data matrix, estimating the parameters, changing the motions as you move. And the controller, which is, we talked about inverse dynamics controller canceling out the original terms. The controller is actually changing the parameters that it is canceling as the estimate dials in. And there's a beautiful world of adaptive control that talk about the stability of the original controller, the stability of your recursive least squares estimator that's trying to estimate the data and trying to make guarantees that your total system will achieve its, will not only be stable, but will converge on the optimal estimation, or well, the optimal performance, the optimal tracking control, possibly sacrificing estimation quality, but because your goal is just to track trajectories. And that is some of the best results that we've seen from the adaptive control world, right? So Jean-Jacques got a great class on adaptive control on robotics and talks about this and does beautiful online estimation of parameters. And I'll just end by showing you some of his other, this is not only the throwing, but he did catching. Okay. Throw it back through the hoop, let's say. And my favorite one, which I don't know, I'm not sure if this was ever a paper. I remember asking him at one point, and I think he said he didn't actually publish it, but they were able to do exquisite control with these online adaptive controllers to like estimate the dynamics of the airplane as it's flying and then snatch it out of the air, right? I should say the multibody equations feel limiting. The airplane has aerodynamics, right? So what happened there, I'll pause that just because that's distracting, okay? But back in the day of doing this model reference adaptive control, they would put in a residual network, if you will, with linear basis functions and still do least squares in order to do this estimation and get pretty surprisingly good results even for complicated systems like that. So if you put like a radial basis function network here or something like that, then you can actually still do least squares and capture residual terms that were not in your original multibody equations. Yeah? Yeah, so they actually, this was like before computer vision, right? Right? So they had foveating cameras in the corner of the lab. Okay, so you'll see a lot of times there's like a bright white thing or a bright orange ball being caught. Okay, so imagine cameras on actuators in the corner of the lab, trying to keep the bright orange ball in the middle of the sensor. It's called foveating, just like your eyes foveate. Yeah. So it's moving the cameras to track the ball, and then the encoders in the cameras tell you where the ball must be. You can back that out. Yeah. So it's didn't solve computer vision, but did a pretty good job. Yeah. Yeah. Awesome. Okay. See you next time. Yeah.